Everyone. In this video, we are going to discuss the topic of testing of DC motors. Mainly there are going to be three types of tests that I'm going to cover. One is the brake test, and the second one is what is known as Swinburne's test, and the third one is Hopkinson's test. So the purpose of these tests is to find out the performance of the DC motors. What are its losses under various loading conditions? How this DC motors losses will change and efficiency will change and so on. So that is the main purpose of conducting these tests. So basically, when you are manufacturer, you are manufacturing a DC motor, then you would like to know how this motor performs for different loading levels and so on. So for that you conduct these tests. So one by one let's look at these tests and we will see how these things come up. So we'll begin by brake test. I suggest we basically break the DC machine and then try to find the input and output. So let me explain it further. Brake test. So uh, consider it like a DC machine here. So it's a motor. Excuse me. It's a motor. So now for this motor, the input is electrical. So I'm not drawing a circuit diagram, but basically I'm drawing a block diagram kind of thing. And the output, there is a shaft, and then there is a uh, shaft which is coming out of the motor where the output is mechanical. So at the input, I give a voltage supply and then a current. So I have this current and then voltage, which together will become the input power. So P input is nothing but the DC voltage multiplied by the DC current. This will be in watts. So you'll get the input power here. Now, what is the output? Now, at the output, I can have, so this is basically a side view. So at the output, I can attach some kind of a pulley system. So this is mechanically attached here. And then we know the radius of this. So let's say the radius of this is R. And on top of this pulley system, I attach a belt. So I have some kind of a fixed structure at the top. And on top of it, I have W1 and W2. Two spring weights, and then there is a belt which is wrapped around this. So like this. So since this is the side view, uh, I'm not able to draw it properly, but then let's look at the end view. So end view of the same, it looks like this. This is a, so let me use a similar color. This is the pulley of radius R, and then on top of it, I have the this ceiling is fixed. I have a spring balance W1 and spring balance W2, and then this is firmly fixed to the top, and then there is a screw fitting here. I can tighten this or I can loosen this belt, so the belt will be like this. So this is the belt. Now imagine the normal case where I release the belt so that it is not very tight. So when the motor is started, that means when I apply voltage and current, the motor starts taking the electrical input and generates a mechanical output, and then the pulley starts rotating. Because the belt is not very tight, we haven't applied any brakes, so to speak. So it rotates under no load condition at some no load speed. But then the moment I start tightening the screws, then there will be more and more weight that is or pressure that is falling on this particular belt, and then the speed will reduce. So you had seen that in case of a DC shunt motor, as the load increases, speed reduces. So I will choose. So now imagine that this is the direction of rotation. So let's say the direction of rotation is clockwise. When the motor is rotating clockwise, the force, uh, that is whatever we see here on W2 will be more than the what we see at W1, because this is rotating. So, or okay, so just to be consistent with the formula, let's imagine that this is rotating in the anti-clockwise direction. In that case, I'm sorry, anti-clockwise will be like this. In that case, the reading of W1 will be more and W2. So these are spring balance. So spring balance is basically, if I attach a weight here, 10 kgs weight, here there will be a pointer which shows that the weight is 10 kgs. So this is something like that. So this spring balance will read a higher weight, and this spring balance will read a lesser weight when this motor is rotating in the anti-clockwise direction. So, I mean, it's in general, it's just, you can call it one or two, anything. If you find that the motor is rotating in a clockwise direction, then you can designate this as W1 and this as W2. It doesn't make a difference in that case. Now, the objective is, I have this input here. This is the electrical input. This is in watts. So W is the unit here. Now, what is the mechanical output? So we know that mechanical output power, P out, is nothing but torque at the shaft multiplied by omega. Omega is the angular velocity of the rotor. Now, what is the angular velocity? Omega. So omega is angular velocity of whatever this rotating part of the machine, to say pulley. So this will be nothing but 2 pi n divided by 60, because this is, it should be in radians per second. So n is the speed in revolutions per minute. So I divided by 60, then it will be revolutions per second. And then for one revolution there are 2 pi radians. So therefore by multiplying with 2 pi, I get the omega as 2 pi n radians per second. So that I can substitute here. But what is the torque? So torque at the shaft is nothing but force into radius. So this is nothing but force into radius. So this is the general mechanical engineering formula for any rotating object. If you want to know what is the torque, then you find what is the force acting on it and at how much radius distance it is acting, then you can know that. So force has to be in newtons and radius has to be in meters. So this Newton meters is the unit for this. Now, radius anyway we can measure it. Force, how do you measure it? So when I have these two readings, what is W1 and W2, they are in kgs. So kgs has to be converted into newtons. So 9.81 multiplied by W1 minus W2 multiplied by R will give me the complete shaft torque in Newton meters. So just I have substituted in the place of force. So the difference of the force is the net force acting on the shaft, which is the braking force. So basically this is the braking force acting on shaft. Of course, that is only this part. Now when you multiply it with R, then you will get the shaft torque, and then I have the omega. So substituting everything, I'll get P out is equal to torque into omega. So 9.81 W1 minus W2 multiplied by R multiplied by 2 pi n divided by 60. So this is the entire uh, expression. So, but then we have some constants. So 9.81, 2 pi, and then 60. So all these things are there here. So it turns out that if I simplify that, then I'll get, so this will be 1.027 into W1 minus W2 into Rn. So this is my output power. So again the units will be watts. Now, so what is the experiment about? So first you take the machine, then you connect the voltmeter and ammeter. So here you connect a voltmeter, and here in series you connect an ammeter. So you measure voltage and current, you have got the input power. Now coming to the load side, you measure W1 and W2, you measure the radians, and you measure the speed at which the rotor is rotating. So to measure the speed, there is a tacho generator instrument, tachometer I think it is called, to measure the speed. So once you have all these, so I can find out efficiency. Efficiency is output by input. So using that we can find the efficiency of the motor. So let's solve one example problem on this particular brake test so that we get our understanding more firmer. Here is the example on this brake test. Okay, so let's look at this question. You can try solving this on your own, or you can just go through this video where I'll continue to answer it. So the question is like this. A brake test is conducted on a DC motor. This, the spring balance readings are 10 kgs and 35 kgs. So because the brake test, it will have two spring balances. So the difference is the total force that is acting on the DC motor. That will be in kgs, you have to convert in newtons. All the things we have just discussed above. So the diameter of the drum is 40 centimeters. So let me write down the data. So W1 is 10 kg, W2 is 35 kg. Actually, this should be W2 and this should be W1, because the one which is higher we consider, just to be consistent with the formula. It doesn't matter. What we are interested in is the difference between the weights that are there here. And the diameter of the drum is 40 centimeters. Therefore, radius will be 40 centimeters divided by 2. And if I convert to meters, it will be 20 centimeters, or it will be 0.2 meters. So be careful with the units. Here it will be in meters. The speed of the motor under loading is 950 rpm. So N value is given 950 revolutions per minute. When supplied at 200 volts, taking current of 30 amperes. So therefore I already know what is input power, P in. So the input power is nothing but V into I, which is nothing but 200 into 30, which is nothing but 6000 watts. Now, what else? What happens when the belt? All right, I think we'll have to solve this later. What happens when the belt is slightly tightened? And I forgot to mention what is the efficiency as a part of the question. So find efficiency. So let me add it here. Find efficiency at this point, and then what happens when the belt is slightly tightened? Okay, so let's get going. So now, after having calculated the input, so let's focus on the output side. So we already worked out the formula. So what is that? P out is 1.027 W1 minus W2 into Rn. So that is what we had just written here, 1.027 W1 minus W2 into Rn, which is derived earlier. So let's go forward. So this is 35 minus 10, and the radius is 0.2, and then the speed is 950. So if I do this calculation, so the value is 4878 watts. So now I have the input and output. Now I can find the efficiency. Efficiency is power output divided by power input. So 4878 watts divided by 6000 watts. so which gives me an efficiency of about 81.3%. So when you actually do this calculation, you get 0.813, and if I express it in the percentage, it will be 81.3% as the efficiency of the motor. So this way, just by conducting a simple brake test, I can determine the efficiency of the motor. And if I do a similar test for another machine, then I can compare both the machines and say which machine is more efficient and less losses and so on. So certain practical things here. So what is it? What happens when the belt is slightly tightened? So let me go to the diagram. Now, if I use this particular screw and then tighten this particular belt on this thing. So right now it is rotating at the speed of 950 RPM. If I tighten the belt, what is the consequence of it? Because the belt is tightened, more load is coming on this particular motor. That means more braking effect is there. That's why it is called brake test. Therefore, the rotor will slow down. So the omega will reduce. That means this omega will reduce, but then the shaft torque will have to increase to match the difference now. The difference will widen. Earlier it was 10 kgs and 35 kgs, so difference being 25 kgs. But now because the belt is now more tighter, more force has to be there. So the difference will widen, and therefore the output power will increase. Now on the input side, the voltage is anyway constant, which is the supply voltage we are maintaining constant at 200 volts, for example. Instead of 30 amperes, now maybe 35 amperes or more current will start flowing into the machine. So as a result, there will be more I square R losses in the motor. So motor starts heating up. So it has heat energy lost here. Similarly, not only the heating, there is also another major heating that is happening here. See, the belt is fixed, whereas the rotor is rotating inside that. So there is going to be enormous friction between the belt and the rotor. So typically the cooling has to be there. So the normal arrangement of what they do in the laboratory is to have some kind of a drum kind of a structure inside which there is a some space to put some water. So you actually pour some water into that the drum of this, and when the belt and the drum uh, move across each other, there is a friction, and that friction will heat the water, or in other words, the water will cool the drum, and water evaporates and not evaporates, water actually converts into steam, boils, and then goes off. So that is one way to control the temperature of this particular drum system. So these are all some practical aspects which come with doing the brake test. So if in your life, if you have a chance to visit a laboratory in a university or outside in industry or anywhere where there is a, DC motor and there's a equipment set up to test the braking, conduct this brake test, do make use of that opportunity and try to conduct a test or yourself on a DC machine. Let's continue. For the sake of practice, let's work out one more quick example. So all the data that you require for this brake test is already given here on the screen. So just go through this data, pause this video, and then you try to find the efficiency based on the data that is there. So try it yourself, and then you can always compare your answer with the answer that we'll get here. So let me begin here. As usual, you know that we can find out the input power. So in the given data, if you see, the current is given and the voltage is given. So 10 into 100, 10 amperes into 100 volts will give me the 1000 watts as the input power going into the machine. So that way it will become easy for calculate the efficiency, because in the denominator we have 1000, so it is easy to calculate. Anyway, that's a minor point. What is a P output? So we had already worked out the formula 1.027 multiplied by W1 minus W2 and multiplied by Rn. So all the data is given 1.027 multiplied by what is W1 minus W2. So 9.1 minus 0.8. And then the radius, notice the radius is given in centimeters, so convert into meters. So 7.5 divided by 100, and then the speed is given 1320 rpm. 1320 rpm. So before we move forward, see, how do you know when to stop this particular uh, experiment at the time of tightening the screws? So when you're tightening the screw this across this belt, so the belt keeps on getting tighter, and then the this gap keeps on increasing. But when do you know you should stop, so that you are actually getting the efficiency of the motor at full load? So for example, you want to find efficiency at full load. So you know what is the full load rating of the machine, how much current it can take. So you keep looking at the ammeter, and sometimes it shows 3 amperes, 4 amperes, 5 amperes, and so on. And you will keep on tightening the screw until the current reaches 10 amperes. Then you are certain that the input is rated. So now you can find that at that full load what is the output. So anyway, that's another detail. So let's simplify this. So when you simplify this, I believe you will be getting something like 844 watts. So I have to check this calculation, but then this based on quick view, I got this. So now you can find the efficiency. Efficiency is nothing but output by input. So 844 divided by 1000. So that is nothing but 0.844, or you get 84.4% efficiency. So this is about efficiency calculation. So in brief, we had looked at the one of the tests, that is brake test, and how the brake test is conducted. You measure the input and you measure the output, and then basically you calculate the efficiency. So this is the one of the tests for this. So just to conclude this topic, let me briefly write down what are the advantages of brake test. So the advantages of brake test include that you are actually, the motor is actually loaded. So the motor is actually loaded. That means it actually consumes that much power. So we get efficiency under loaded conditions. That's one of the advantage. And the second advantage is it is simple and easy to perform. Simple and easy. So you had seen the method involves connecting a voltage and then connecting a disconnecting the armature, that is the input side, and the output side you have this belt system. Of course, you should have all the equipment, and it is easy to confirm. And you can also find the efficiency at various levels of loading. That means I can start with no load, and gradually I can keep on increasing load, and I can keep finding. I can also get a curve, something like load versus efficiency. So you might notice that the efficiency of the motor under zero load is anyway zero. So it keeps on increasing, and after a while it falls down. So this kind of phenomenon also you can kind of find using this thing. So what are the disadvantages, or what are the, I mean, strictly speaking, they are not disadvantages, but what are the things that we need to consider? So of the brake test. So one is that it has a lot of losses and heat. So because you are physically tightening the belt and all, there's a lot of friction. Therefore, due to friction, so therefore you have to go for cooling. Cooling is compulsory or necessary. And the another point is that it is suitable for small machines. So machines like 2 kilowatt machine or 1 kilowatt machine, or sometimes maybe if you can afford it to have that much heat and cooling systems, you can go all the way up to 5 kilowatt machines or so. Uh, small capacity machines, small rating machines. You can test like this. So, but then if you have a very 50 kilowatt DC machine and you want to test, find the efficiency and all, you can't afford to have a belt and then it generates a lot of heat and all these things. So it is suitable for a smaller machine. Uh, Another thing is the power input power is actually wasted. So input power is wasted. So earlier we had seen this voltage was 10 and current and voltage was 100, current was 10. The entire 1000 watts is wasted. So you can that aspect is there. But then if you conduct this test quickly and then switch off the supply and everything, take one reading, you can avoid this wastage. Okay, so to get back, so we had just discussed the brake test. So let's talk next about the Swinburne's test, and then we'll go later to Hopkinson test. Let's continue. Okay, so now we come to the second test, that is the Swinburne test. So the Swinburne test is classified as a non-loading test. So what is the meaning of a non-loading test is we actually don't load the machine. Without even loading the machine, I'll be studying the machine under no load, and from that information I can estimate what would be the efficiency of the machine at different loads, like 30% load or 70% load or 100% load and so on. So the idea is to do some kind of testing on the DC motor at no load, and through that data estimate the efficiency at any amount of load. So right away you can say that this kind of testing is suitable for very large machines. So for very large machines I can do this. Obviously when I say no load, so it is not suitable for series motors. And the reason is obvious. You all know that series motor cannot be operated under no load conditions because it generates huge speeds under no load conditions, as you have known the theory of series motor. But anyway, this is suitable for shunt motors. So let's look at the connections for this particular test. So what we yeah what we do is, once we have a supply, in series with the supply, I connect a variable resistor, and then this goes to the armature of the machine. So for the time being, let's say this is the motor. By the way, you can connect this. You can conduct this experiment for generator also. We'll discuss that later. Now the same voltage again with a different variable resistor, I can connect to the field winding of this machine. So as you know, the motor will have two terminals for armature and two terminals for the field. Now this is the supply voltage, and let's say this is my armature current. So to measure, I can keep an ammeter here, and this ammeter will measure the current. Let's call it IA0. So basically there is no load, no mechanical load. So I'll write that no mechanical load. So the machine is running under no load condition, whereas the electrical input is given here. And to measure the voltage, I'll connect a voltmeter here, like this. So this voltage exactly measures the voltage that is going to the armature, and here I'm measuring the current that is going into the armature. Similarly, I can also have one more ammeter here to measure the current in the field. So this, let's call it as IF. IF is the current measured here, and let's call this voltage as something like V naught. By the way, I have not mentioned what is the purpose of doing this test. Okay, so let me write that here. Purpose, I just mentioned by word, but let me write it here. to determine constant losses of machine so that we can estimate efficiency at any load. So we'll see how that is done. So let's discuss this further. So let's look at what is the input going to the motor. So the input going to the motor is nothing but just input to the armature only. If you look at it, so uh, input to armature. Since you are measuring these two, I can directly find that that is VA. Let's call this as VA, and then IA naught. Then now this input, what happens to this input is that there are losses. So what are the losses? Losses is nothing but armature copper losses plus iron losses plus friction and windage losses. You all know this. For a DC machine, you know that all these losses are occurring. Now in this case, now this I can combine, and this part will not change. Iron losses, as long as the motor is running under rated speed, the iron losses will be same, and the friction losses also will be same when the motor is running at the rated speed. So therefore, this part now, if I, by the way, what is the output here? So here, uh, P out is 0. So because there is no mechanical load, so all the entire input is exactly equal to losses. So what is the armature copper losses? So you see, armature copper losses is nothing but P input is equal to, armature copper losses will be nothing but Ia square Ra. This is the armature copper losses plus, let's call this as Pi iron losses plus PFW friction and windage losses. So like this. Now I can measure this part, and notice that here I am not using IA naught. So IA naught I am not using because I want to estimate what will be the this part, iron losses and friction losses, under full load conditions. So under full load conditions, armature input I know, armature current I know. Now armature resistance I can always measure. I can just take a ohm meter, connect to the armature terminals, and measure the resistance of the winding, and I can know all these things. So from all these things, I can find out the losses. Now, apart from this, there is also the losses in the shunt winding. So, what are the losses in the shunt winding? So, losses in the shunt winding, if I go back here, there is a shunt field winding. I can measure the shunt field current IF, and also I can measure the resistance RF. So, how to measure the resistance? Again, the same process. You just take a resistance measurement instrument, an ohm meter, and measure the resistance. So from that, losses in the shunt winding is nothing but the copper losses. So that is nothing but IF square RF. Now you see here, this branch is completely independent. So irrespective of the loading of the machine, the shunt losses also are always constant. So if I want to know total constant losses, so what are the constant losses here is this part plus the shunt field winding. Uh, Maybe I'll draw a diagram to keep it more easy to understand. See, the diagram sometime back we had discussed it in a different context. So this is the motor. So this is the electrical input. Of course, you can draw the diagram in a different way also. This is the mechanical output. So what is the electrical input? This is nothing but V into I. So this is nothing but the line voltage into line current. Now once the electrical input is there, I can split the losses. So here I can go for copper losses. So one part of the copper loss is Ia square Ra. This is the armature copper loss. Another part of the copper loss is ISH square RSH or IF square RF, whatever is the notation. So these two in addition will give me the total copper loss. What is this one? This is actually nothing but the mechanical power developed, PM. So this is internal to the machine. This will be nothing but back EMF multiplied by the armature current. This also we had discussed earlier. Now, at this point, there will be another loss. Okay, so that is the iron and windage and friction losses. So, remaining that whatever is there, that is nothing but your P output. Now, in terms of saying this is constant, and so this is constant, and this one is also constant. Or let me, in other words, write like this. I'll just combine these two and this call it as constant losses. And this one is basically the variable loss. So the constant losses and variable losses, if I once again combine them, okay, so I'll get the total losses. This is total loss. And if I combine the total losses and the output, that value will be equal to the input. So something like this. So I hope this figure is making some sense. So based on this, we can get the efficiency. So this is the input, and then power given to the armature, and then the mechanical power developed, and then some power coming to the shaft of the machine, output power. So the output power is nothing but torque into shaft torque into omega. So anyway, we'll now based on this separation of variable constant losses, we'll analyze the Swinburne test. Having discussed this map, let's go up and then see. So actually there is a small change here. This is supposed to be IA0 only. So let's review it once again. We have this voltage and then we have a variable resistance in series with the armature winding. But then this resistance, why do we need this? See, under normal operation, when the machine is loaded, it slows down. And at the rated full load conditions, the machine is actually running slower than the no load. But then at the no load conditions itself, I want to run the machine at that speed which corresponds to the full load speed. So therefore, I will have to apply a reduced voltage. So that's why this resistance is there, which will slightly drop some voltage, and the remaining voltage VA will get applied to the armature. So that's the reason for having this. And what the reason for having this is again to adjust the field current to the rated value, so that even under no load condition, the full load speed is maintained. So that is the one thing here. And as discussed earlier, the input is VA into IA naught. Input, there is only input to only the armature, but then the losses that are happening in this diagram are nothing but the armature copper loss, which is IA naught square, that is the current that is flowing here, into RA, plus PI plus PF2. This part is unknown actually. P in I can actually measure because I am measuring these two quantities, and RA I can measure. So therefore, From all of these, I can find out what is Pi plus Pfw. That is one part of the constant loss. The other part of the constant loss in the shunt winding is this one, or in other words, I am just using ISH, RSH. So this is just instead of RF field winding resistance, I am saying shunt field winding resistance. It's just nothing but a notation. So therefore, if I add this part and this part, I get the total losses. So first, let me get this part here. So what is Pi plus Pfw? That is iron, friction, and windage losses. So that is nothing but P in. That is nothing but Va Ia naught minus Ia naught square Ra. So this is one part of it. So let's call this A and this is B. So A plus B will be the total losses of the machine. Total constant loss of the machine. So that's what this one plus this one, the total constant loss. So total constant loss is nothing but, let's define it as P const is nothing but, let me add these two quantities, that is nothing but Va Ia0 is the input minus Ia0 square Ra. So this part is the iron and windage losses under full load speed plus the shunt ISH square RSH. This is the shunt copper loss. So this is the total in the constant losses. So this part we have covered. What about the variable loss Ia square Ra? So total variable loss P var, let's call it as, is nothing but Ia square Ra as seen in this diagram above. So now I have the total loss of the machine. So PL is the total loss. So VA, IA, I just add these two. So this is the idea proposed by the Swinburne to determine the total loss of the machine. Now, given the losses, I have an expression for losses. I can simply plug in these values. So only IA, this part will be varying. This is anyway constant. So I can just vary IA, and then for any value of IA, I can find out total losses. And I also know the input. So therefore, I can find the efficiency. So in fact, you can do it for both. So let's say you're talking about motor, as the diagram shows above. In the case of motor, what we are doing, so now under full load condition, and I just have to measure this voltage and this current. Then I can have motor here, then I can have like this. So here, this current will be the ISH current, this current will be the armature current, this current will be the line current. So I know input, P input is nothing but voltage into IL. This is the total for the motor. Whereas the losses, for that IA I have to use IL minus ISH. That's it. And then once I know IA, I can know IL. IL is nothing but function of IA. And then I have other quantities which are all already determined. So this is in the case of motor. So once I know input and losses, so efficiency is nothing but 1 minus losses by input. Right? So this is nothing but efficiency in terms of fraction, but then efficiency percent you multiply it with 100. So this is in the case of motor. Now what happens in the case of generator? So you have generator, then so here there is a load. So you measure the load current, this is IL, and you measure the load voltage. So let me complete the circuit again. This is generator. So this is ISH, and this is the mechanical input, and this is the electrical output as you have seen. This is a generator. So in this case, what is the IA? So in this case, IA will be nothing but ISH plus IL. So you measure IL and you measure ISH. You can add these two to get what is IA. And once you have IA, I can find the power losses. And once you have power losses, what is the power output here? So the output I am getting here will be P into IL. So P out is nothing but P into IL. So once I have the output, then I can find the efficiency. So efficiency is nothing but output divided by output plus losses. So I can use this formula to get that. So this is the one of the ways in which you can do the Swinburne's test. So we'll try to solve an example problem based on this. So for that, let me just find the example problem and then we'll solve it. Here is an example problem on Swinburne's test. So as you know, Swinburne test is a no-load test, and some information is given to you. Based on this, please pause this video, try to solve it based on what we discussed, and you can later cross-check your answers. So meanwhile, let me now attempt to solve this. So look at the data that is given. 400 volts. So this is the voltage that is applied to the entire machine, to the both armature winding and the field winding. And on no load, the current taken is 5 amperes. So therefore, when the machine is under no load, then 400 into 5 will be this. So let me draw the diagram for it so that you can understand this better. So we have this is RA, armature resistance, and this is the field winding. Here we are applying 400 volts. When 400 volts applied under no load condition, then the no load current here that is taken is 5 amperes. So this is the denoted as I naught. Meanwhile, RA is 0.5 ohms and RSH is 200 ohms. So from this, I can right away calculate the field current, so or shunt field current. That will be nothing but 400 divided by 200. So voltage divided by resistance will give me the current. That is nothing but 2 amperes. So 2 amperes anyway is flowing here. So out of 5, 2 is flowing. The remaining 3 amperes will obviously flowing in the armature. So this is nothing but IA. So the armature current is 3 amperes. I naught minus ISH. So this is nothing but 5 minus 2. So this is nothing but 3 amperes. So given this, now I can find out. See, my objective is to find the friction and windage losses. So look here. So what is the input? Power input is nothing but 400 into 5. So this is nothing but 2000 watts. What is the copper loss? Is nothing but IA square RA plus ISH square RSH. So this is the armature copper loss, shunt field copper, and all the values are known. So 3 square into 0.5 plus 2 square into 200. So 3 square is 9, half of 9 is 4.5. 2 square is 4, 4 into 200 is 800. So you're getting 804.5 watts. This is the total copper loss. Therefore, the remaining one, see, this is the input and this is the copper loss. So the remaining one is nothing but iron and friction windage losses. The total losses there is nothing but 2000 minus 804.5. So basically I am getting, what is this, 2000, so let me use my calculator. 2000 minus 804.5. So 1195.5 is my iron and windage losses. Now this part is fixed and this part is fixed. So therefore only variable part will be the armature current. So let's go back and okay, if I look at the question once again, here I full load is 50 amperes. So now under full load condition, so this is under no load conditions. Swinburne's test is conducted here. Now under full load conditions, what happens? I'm running out of space, but let me see. This is under full load. So then you have 50 amperes flowing here, and this is the armature. We have armature resistance 0.5 ohms. Then we have the armature here, and here the field winding is there, which is 200 ohms. So therefore this current is anyway 2 amperes already, we already calculated. So this current will be 48 amperes for the motor. So under full load conditions, what is the copper losses? So armature copper losses under full load condition. So that will be P copper or full load copper loss. Ia square Ra plus ISH square RSH. So this part is anyway same, 2 square into 200. This is, now this one will be different, 48 square into 0.5. So let's do that. So 48 into 48 into 0.5. So 1152. So here I am getting 1152 plus this is 4 into this is 800. So this total will be 1952 watts. Now the total losses will be nothing but 1195.5 plus 1952. So how much is that? Plus 1195.5. So 2347.5. 2347.5. So I'll just round it off to 2348 watts. So once I know the total losses, I can find the efficiency. So apologies for cramping everything here. So efficiency will be what? So I know the losses. Do I know the input? Yes, I know the input. 400 volts. So here the input voltage is 400 volts. So from that input voltage, I can always multiply this. 400 into 50 will be 20,000 watts. So that is the input. So, or I can do 1 minus 1952. I'm sorry, 2348. 2348 divided by 20,000. So divided by 20,000. So minus 1. So this is 88.26. So this way I can find the efficiency of the motor just using the Swinburne's test analogy. So let me use the drawing above to just show to understand this example better. So what was our input? 400. Let me use different colors. So this is the example data. So 400 into 50. So here I'm getting 20,000. So the armature copper losses are 48 square into 0.5. So how much is that? 48 into 48 into 0.5. So yeah, we already calculated this. This is 1152. So this part we already covered, 1152. And what is the shunt losses? This was 800 watts. And this is 1152 watts. And what was this one? This one is iron losses, and that also we calculated. That was 1195.5. So this is 1195.5 watts. So now from 20,000 I subtract these two quantities, then I subtract these two quantities, then I get the output power. So all these things we can actually work out. We have added these two as a total copper loss, or so this is total copper loss, or we can add these two as total constant and variable. All these combinations are possible. So then finally we get the output. So we can actually work out that. So I hope you got some things from this. So let's continue.